Hello again and welcome. Today we're going to be going over the software interface for the BM788BT. Brymen's agreed to make that documentation public domain, basically allowing third parties to develop software for their products. They provided me with an early copy of that specification, and I've been working with them while I've been developing my own software for this meter to correct any problems. Now this isn't anything new. I've written software for these three meters here as well. On the left, this is the Unity UT181A. This is the EEVBLOG 121GW. And of course on the right, this is the Gaussian MetraHit Ultra. All these support Bluetooth. Now the software that I wrote for these three meters, I did all that using LabView. Now LabView does have a built-in library for Bluetooth. Unfortunately, all these meters use BLE, or the low energy Bluetooth. That's completely different than the standard Bluetooth, and LabView does not have support for that. Now, of course, LabView is written by National Instruments, or NI now as they want to be known as. And I just recently checked their site, and it seems they're more interested in integrating AI with LabView rather than putting features in like BLE, something that I could actually use to talk to test equipment. To me, that company's kind of gone off the rails, and I'm certainly not recommending that you run out and buy a copy of LabView. I think now for a perpetual license of the professional version of LabView, you're looking at about 10 grand. That's actually cheaper than what they first reintroduced the perpetual license at $15,000. So yeah, you're saving a whopping $5,000 for the privilege to use their software, which doesn't support BLE. These are some of the tools that I've used in the past for my BLE development. This is produced by Adafruit. You can see this is the Bluetooth LE sniffer. So this is a standard dongle that has some custom firmware written for it that allows this to sniff BLE traffic using Wireshark. So I actually use this to help develop the software for this meter as well as the UT181A. So to work around this whole BLE LabView problem, there was a company that produced a third-party library for LabView, and the way that worked, they wrote it specifically for this particular radio. Now this is made by BlueGiga, and this device shows up as a standard RS-232 port. So when I wrote my software, I based it on that library, and it worked fine for these three meters. Now in the case of the 121GW and this MetraHit, the software interface for these two, that's basically open source. The interface for this UT181A, again, this comes with a separate Bluetooth radio adapter. This is a model UTD07A. They have a newer version of this now. When I purchased this, they claimed that they had support for Windows. That was not true. So I had used this sniffer that I showed you to reverse engineer the protocol on this. I had a lot of that work done, and then I ran into some other people that had followed a similar path. So they were a big help in getting that software written a lot faster than it would have taken me to continue to reverse engineer it. Now in the case of the Brymen BM788BT, again I had the documentation that told me how to interface to it, so you'd think it would be a fairly easy task. But the first thing that I noticed is when I started communicating with the meter is that it was not compatible with this BlueGiga radio. Again, I could actually communicate with this meter using this radio, but I couldn't get it to transfer any data. And that's because this meter uses a much larger MTU, or basically the amount of data that you can send on a packet. These three meters use the minimum that BLE supports. This exceeds that by quite a bit. Unfortunately, their library that they wrote for this radio, that only supported the bare basic MTU sizes. So to work around this, that same group that had developed the library for the BlueGiga radio developed another one that uses the standard Windows drivers. Unfortunately, they had released that for LabView 2020, 32-bit. Now, I've got a version of LabView 2011. That's all I have a license for. So what I did is I took their library and I saved that for my version of LabView. So basically, we downgraded from 2020 to 2011. So that library is using this common DLL, and it's written in C#, and they're using .NET 4.0. But it turns out 2011 was written prior to 4.0. There is a workaround. Essentially, you end up creating a text file, which is a configuration file, and you place that next to the LabView executable. And then when you load in LabView, it sees that specific file and allows it to load in .NET 4 files. So for this demonstration today, I've just got a BLE 4.0 standard radio. Mine's made by Targus. Got a couple of these, they work fine. But basically any BLE that's supported by Windows 10 in this case will be supported by this library that I'm talking about. So I have a couple of tablets that I use for testing. This one is made by New Vision. It's a Windows 10 tablet, and then this one's made by Lenovo. This one runs Windows 8. Both of these have an Atom quad-core processor. They weren't very expensive. This one I've actually used on my motorcycle as a data logger. So this particular one has actually been at well over 100 miles an hour on my strapped to my motorcycle. What's kind of cool about this one is it has a GPS receiver built into it. But this one here is no frills. I don't remember what I paid for these. It was certainly under $100, maybe $80, $60, something like that. Wasn't a whole lot back then. I bought two. The original one is still running. I just recently upgraded this one to the latest version of 10 so I could download the software for the 121GW and try it. But the software that I'm going to be going over today would certainly run on these two tablets without any issue. So this is the New Vision tablet. You just go under settings, and here we can turn on the radio. So let's go ahead and we'll turn on these meters. And let's go ahead and we'll turn on the Bluetooth. So all those meters are now running. And here we can see it found the BM788BT, and it says it's paired with it. Let's do add a device and Bluetooth. Oh, there's our 121GW. There's the MetroHit Ultra. And here's our Unity UTD07A. So all four meters are now online. Now again, just because we can link and pair to these, all these meters require custom software, and all these protocols are different, so they all require unique software to communicate with them. So just the fact that I can use this device to pair up with this Brymen meter doesn't mean that that's all there is to the problem, right? We have to write custom software for this. So that's what I'd like to go over in this video, is basically I want to show you my source code and explain how all that works and go over their documentation, and I'll give you a demonstration of how that works. So I'll go ahead and set that up. So a few people asked about using Bluetooth with the 3 AAA batteries. Again, these are the ones that were supplied with the meter. So what I did is I set up my PC where it's basically just sniffing traffic from the meter, and I was plotting the RISI, which is essentially the signal strength off of this meter. So I lowered the battery voltage while monitoring the signal strength, and I took it down to where the low battery indicator came on, and then I took it all the way down to I think like 2.5 volts where the meter finally dropped out. At that point, the field strength coming off of the radio on this was basically the same. Now I ended up calculating I think about 120 hours of operation with this. Now again, these were the batteries that they supplied with this meter, and I tested this meter for about a week, and it wasn't on 24/7, but it had quite a few hours of operation. And what ended up happening is I was running a long-term test. I wanted to make sure that there were no other problems with the meter disconnecting over a longer time. So I ran a test at like about 6 hours. There were no issues with that, but I thought I'd set it up for a 24-hour run. And after a little over 15 hours, when I came back and I checked the data, and the meter had powered off. And so I turned the meter back on, and the low battery indicator was not on at that point. And I turned Bluetooth back on, and it started spitting out data again. But then I noticed that the low battery indicator was starting to flicker. So it's interesting, if you put these batteries in there and you were not running Bluetooth, the low battery indicator is not going to be active. So turning on Bluetooth, it does draw a little bit more current, but if you wanted to run 24/7 with the meter, expect, about 100 to 120 hours of operation, which I think is acceptable. I'm not normally going to run a long-term study like that using a handheld meter. I've got bench meters that are attached to the Ethernet port if I want to run long-term tests. This is looking at the original library that I used Again, this library was based on the BlueTooth BLE 112 USB dongle. Let me just go ahead and fire up my software that uses this dongle. We can go ahead and start this. So currently this is scanning for advertisements. Let's go ahead and we'll turn on the BM788BT and we'll activate the Bluetooth. And you can see it shows up. So this is the advertisement. This is their latest specification. And this is how you would decode that advertisement packet. So we can see it starts with a 216, and that's the bytes here, 216. We have the advertisement length, which is an 8. And then we have a 9, which is the don't care. And then we have the BM788BT. So let's try scanning the meters. So the scanning, we're going to look for all these devices and build up a table. So let's just stop the sniffer. And we'll go to scan. So these are the devices. You can see these are all public. We could plug in the MAC address for the device that we want to target. So in this case, I know that the BB80507897, this happens to be the Brymen BM788BT. So I'll just go ahead and hit stop, and then we'll select connect. So it's gone ahead and connected to the device. Let's select handle. So now this is reading all the handle IDs from that Brymen meter. If we go back to the specification, down here we can see the UUIDs that they're using. So they have two different ones basically that they use. One is for notifications, the other one is to read-write commands to the meter. So this 3CDD4, which we can see right here, this is used to send commands down to the meter. And the first thing that you need to do to communicate with this meter is send down a password. Once you have the meter set up, you set up notifications, and that's done through this characteristic UUID. So I'm sure a few of you are curious why there's so many entries in this handle table when the documentation only calls out basically two different UUIDs. Well, some of those are standard BLE commands, but there's another one in there that it looks like it's actually a specific unique command that probably Brymen came up with. So I asked him about what is that UUID used for. Originally, when I started talking to him about BLE, one of my primary concerns was that a user could actually maybe try to update the firmware of the meter or possibly realign the meter and potentially brick it. So they assured me that that was not a problem, but as I asked them about this last command, they told me that that's actually used to reprogram the firmware of the meter. Now, at first I thought, wow, that's like a big deal. But they said, no, that's just for the BLE radio. They said that they were not going to make that information available to the public. Understandable, because again, you could potentially brick your radio. My advice is if you're going to write custom software to communicate with their meter, I would just stay with the parameters that they've defined in the specification. It shouldn't be any kind of an issue. But again, the problem with using this particular library and that BlueTooth radio is that it doesn't provide for a large enough MTU size. So we can see I'm trying to send down this packet here. So this is the password packet. If we look at their specification, right here is the verify password connection. So this section defines the command response packet. Again, it's 32 bytes long. You can see it starts with an FF0120, and we can see that here, FF0120, and here's our 1. This 151, this is the command that we want to send. So if we slide down here, verify connection password, you can see that's the command 0151. The problem again with this though is that you'll see the response is cut short. You can see the meter is responding with this 81, and we can see here the response packet If it fails, it returns an 8001. So the meter's saying that this packet was invalid. Basically what's happened is we haven't actually transmitted the full 32 bytes because of this radio in the library that we're using. So while I've used this library again to communicate with these 3 meters, it cannot be used to communicate with this new Brymen meter. So to do that, we have to change libraries. So this is, I think, published by the same group, and you can see under description, this example demonstrates on how to use the Windows BLE native library to communicate with the BLE devices. So this library doesn't require any specific radio like the previous one does. The big benefit then is, of course, this allows larger MTU sizes. This library again was written for LabView 2020 32-bit, and it's written in C# 4.0. So what I had to do again with this is save this to the previous version of LabView, which is what I have here. And again, trying to load this into LabView, what happened is it failed. So I found this app note. It says if you want to use .NET 4.0 assemblies in LabView, you must explicitly configure LabView to use a common language runtime 4.0. Open a text editor. Create the configuration file that contains the following text. Save this new configuration file in the same directory as the LabView exe. Name the file labviewexe.config and relaunch LabView. Now that worked until I tried to use the application builder to make an executable, and I ran into the same problem. So I found this other app note. If you're creating an executable application with the .NET 2.0 framework, ensure that there is also a configuration file in the same folder as that executable. This would be the exact same configuration file that was placed next to LabView exe. However, it must be renamed to executable name.exe.config. So all I did is I took that same configuration file, I placed it next to my executable, and that allowed me to execute the 4.0 library. So let's just fire up my application real quick. So this is what it looks like, and let me go ahead and select scan. And here we can see it's found the Brymen meter. What we can do is select devices present, and here you can see it's found 3 different devices. What we're looking for is this manufacturer ID of 131, which again, going back to their documentation, that's these 2 bytes here, and these are fixed at 0131. So once I see that manufacturer ID, I know that this MAC address and this BLE address are for this meter. Now there could be more than one meter. This software doesn't care about that right now. It's just going to go for the very first one that it picks up. Let's go to command responses, and I'm going to select link. So here we've sent down 4 different commands. There was a password request, a device request, model request, and then the BLE firmware version. Let's go to handles. So again, these are the UUIDs that the meter supports. Here we can see the notifier. It's CDD5, and CDD4 is again the command messages. Again, there's no need to pair with the meter. This software is going to handle all that for us. So if we look at notifications, you can see it's recording right now, and you can see we're reading AC volts in the meter set to auto range. Let's just change it to a different mode. So this is DC volts. If we change our selection, this is now AC plus DC, and we can see that in the function. Here's DC only. Let's try changing it to hertz, and we can see it's reading hertz of line, auto range. Let's go to millivolts. This is millivolts AC. Millivolts AC plus DC. And this is logic hertz. And this is duty cycle in hertz. And then we're back to millivolts. Here we are in resistance. You can see it's overranged. I probably have a resistor laying around here. Here I have a S102K. This is a 1 ppm film type resistor. It should read 1 k ohm. And you can see the meter reads 1.000 k ohms. So this is continuity. And here we are in conductance. See, it's reading out in nanosiemens. This is capacitance. Here's our diode check. This is temperature. And that's T1, and here's T2. And here is T1 minus T2. Now, one of the things that's interesting, as you can see, the output rate is running along at about 5 hertz. If I take this down to AC volts, that reads at basically 5 hertz. You can see the update rate is pretty quick. This is an average over the entire amount of packets that we've received. So there's been a total of roughly 900 messages received, or 900 readings. That coincides with this 930 down here. So some of the readings are quite a bit slower. Again, if I go down to milliamps, let's just zoom in on this a little bit. You can see it's updating about 1 time a second. Let's go to microamps. And again, you can see it's about once a second. Again, this is in conductance. Let's go back to resistance. You can see that's quite a bit faster. Again, there's continuity. It slows down quite a bit. And here we are in conductance. And again, we're about at 1 time a second. Let's just try putting a resistor back on here and see if that slows it down. So again, this is our 1 k ohm resistor. And again, you can see it's quite fast. We go to the millivolts. Again, you can see that's updating at basically 5 hertz. And DC voltages, that's again updating at about 5 hertz. And AC volts is also updating at about 5 hertz. Down here we can see the transfer rate. So this is roughly 0.2 times a second, or 5 hertz. You can see that some of the other readings take quite a bit longer, but most of them are basically at 5 hertz. What I'm going to do is just connect the meter to my function generator real quick, and we'll select DC volts. And let's go ahead and we'll plot the reading. I'm just going to clear out the chart real quick. And this is switching, you can see, from plus or minus 1 volt. Now currently the function generator is running at 100 millihertz. Let's go ahead and speed that up a little bit. So here we are at 200 millihertz. And here we are at 300. I'll just zoom into this a little bit further. Here we are at 400, 500, 600, 700, 8, 9, here's 1 hertz. You can see it's starting to alias quite a bit now. This is at 5 hertz. And you can see it's definitely aliased. Of course, the meter's sampling at 5 Hz and we're putting out a 5 Hz waveform. It's asynchronous. Here we are at 4. Good demonstration of aliasing. So if you're curious on how this software works, what I'd like to do next is go over the source code for this and give you an idea, because writing software for this meter really wasn't a big deal. I would say any engineer could probably knock this out pretty quickly, especially with them providing the documentation on the protocol. So it doesn't require any reverse engineering or anything on your part to figure this out. It's all documented. So let's fire up the source code for this. So again, looking at the directory structure, basically when you download this BLib, you'll end up with this DLL. That's what you're making your call to. You'll also have this directory of functions. So this is what's included with that library. Again, all I've done was take these and save them to an earlier version of LabView. But if you have a later version, it would probably work just fine. I just use 2011 because that's what I happen to own. So again, I'm not recommending that you go out and buy LabView. I would assume that most of the people that are writing this kind of software are using Python. So let's just fire up that source code. So this is the entire source code directory right here. Let's just go ahead and open up the project. And this is the main VI, or the main program here. And we can do window and show block diagram. So if we look at the software, there's essentially 2 loops. The one at the bottom is our notification loop. The one at the top is doing all the display. And these communicate by this message queue. So when we start the software up, normally again what we're going to do is scan for the devices. And you can see all I'm doing is making calls to their library. So we start out by initializing the BLE interface. We start the watcher. This is the port sniffer. We collect the data here every half a second, and we're looking for the BM788. If we find that, then we go ahead and stop the loop because we know that the meter's out there, and we turn off that watcher so it's no longer sniffing the data. And then we parse through that data to get our MAC ID and our BLE address. Really, from this regard, there's not a whole lot going on in the software. We're just sniffing the bus using their standard calls and waiting for the BM780 to show up. Once it does, we print the data. Not a lot to it. Next thing we're going to do is connect to the meter. So we select the connect button. We have our BLE address. So we just call this function here, which is connect. We're going to try 5 times. If it does succeed, we stop the loop. And from there, we're going to read all the UUID values from the meter. And that fills out this handler table. We then go through and we send down different commands to the meter. That's this function call here. So I currently send down 4 different commands. Of course, the first one I send is our password request. The next thing I do is request the device, the model, and then the BLE firmware version. So I do that by creating this list of commands. So here you can see I'm just building up these message strings, and again these are all defined in that specification doc. I convert them to a hex string. I run the CRC calculation on that, and then I go ahead and add the header and the footer. Convert that back to a hex string as well, and that becomes my command. I do that for all 4 commands, and then I go ahead and send them out. Down here I'm looking for if any of these failed. If they do, I'll resend the entire message base again. And the way I know it failed is it sends out that 8000 hex, or if the received message length doesn't match the transmit message length, then we know that it failed. Once all 4 messages pass, then I'll stop looping. Again, I'll retry up to 5 times. Once this passes, I just update the device name, model number, and firmware version number. And from there we set up the notifier. So again, this is the notification. You can see it's 3CDD5. That's this guy here. So we set up the notification, and I clear out some of the metrics that we're going to track, and that's basically it. So once that notification has been set up, this loop down here starts to execute. So this looks to see if we have a valid key. If it is valid, we go ahead and pull it out and remove it. That's actually the results from the meter. And I normally parse that a little bit, and I pass that string into this message queue. Now again, that string is 152 bytes long, I believe, right here. So 152 bytes long, but a lot of this data is basically null. So it sends down essentially 5 different packets. One of them is the device information packet. That's 24 bytes long. And then it sends down 4 of these device reading packets. Now the first device reading packet actually contains information, but you'll see here that the others are all null. So this device information packet of 24 bytes is defined here. This contains some useful information, but this second one here, the device reading packet, which is the first of the 3 sent, this contains the information that we're really interested in. So once that information has been captured and it's stored inside of this queue, at every 50 milliseconds I check to see if there is anything in the queue, and if there is, we're going to parse that out. So this bytes and packet is the 152, and again this first 24 bytes is the device information. I don't use that, and then I look for the next 32 bytes, and that's our device reading information. The other 2, we're just going to throw those away. This is where we're printing out the different metrics. This is really the heart of the whole software, and that's this decoder block. So this is taking that reading heading, and we're going to parse through that. To pull up this different information. So again, here we have the function ID, and this is just decoding what mode the meter's in. We just print it to a screen. Down here we have the status flags. Again, that's 3 bytes, and I decode this into a cluster as well as decode it to some different text messages. This is the actual reading coming from the meter. And again, I just decode this the same way that the manual talks about. The only real funky thing with this is we can see that it's a signed number right here, but they manually placed the decimal point. So why they didn't just use floating point for this, I'm not sure. It would take up the same number of bytes, but this is what they've done. So unfortunately for LabView, what it requires me to do is basically manually place that decimal point, which is kind of what's going on with all this. Here you can see our decimal point and our sign. So I have to manually create that string. Here you can see we're putting down the units. I do convert that to a floating point number, and that's what's passed down to basically like plotting the graphs, or if we want to record data to the disk to a CVS file, that's the number that we're using. But the string that's displayed on the main panel, that's this string here. So down here we can see this is the CRC that's embedded in the packet, and here I'm recalculating the CRC and I'm making sure that those two match. I also check the payload for proper start and stop frame, and if those all match up, then I call it a good packet. Once I have all that data, I just print it out. Now again, I'm using the omega sign for my ohms, so I end up having to convert the symbol font from the standard application font. So I just look for that ohm signal, and if I find it, I use the symbol font. So pretty straightforward there. And then again, I take that floating point data, and that's what I'm writing to the waveform. I also do some min-max and mean calculations, and that's calculated based on the history or what is essentially being displayed on the graph at the time. Outside of that, there really isn't anything in this software. You can see this basically is turning on the recording. So I'll store data to a CSV file. You select that button. It basically asks you for a file name. Turns on the record LED, assuming that the file name is valid. And we start storing the data. We can obviously exit the program. This is where we can post-process some of the data, flush the data, or I can add a whole directory or just a waveform. But that's about it. So there really isn't a whole lot to this application. Most of my time on this was spent sorting out that MTU problem. So once I got through that, things started moving along pretty quickly. The only other issues, like I say, I went through this with Brymen, so we've made a couple of corrections to the manual. So what they have available today is pretty close to accurate. The only problem, and I'll show you that right now, is what can happen is the connection can fail. And so down here, if we get this notifier and there isn't anything available, it doesn't matter, we just continue on about our merry way. But if I don't see any data for 4 seconds, then I think that that link has failed. And so I was trying to figure out, how do you recover from this? So I was doing a bunch of different things, and Brymen came back and they said what they do with their Android application is if that link fails, they start sending down the password command to recover from the failed link. And so I tried that, and sure enough, that solved the whole problem. So I've asked them to update that specification to include that little tidbit about how to recover from a failed link. So it's not in their documentation as it stands today, but they are going to include this in the future documentation. Well, I think that's going to be it for this video. Hopefully this helps you understand what it would take to actually write some software to communicate with the meter. Again, it's not a big deal if you want to write a Python script or something to communicate with it and include the meter in some other test application. I think it's very doable thanks to Brymen releasing that information. Again, I'd like to thank Brymen for supplying me with the meter. Well, that's going to be it for the video. Hopefully you enjoyed it. If you have any questions, feel free to leave them in the comments. I'll leave a link to where that BLE library is if you're interested and you already have a copy of LabView and you want to write your own apps. You might find that library helpful. Well, for now, we'll see you in the next video. Later.